Okay, so before we can go over the procedure for diagonalizing a matrix, we need to cover this theorem that justifies the steps that we take. We're going to prove part A, and part B is going to be an immediate consequence of this theorem and what we proved in the last video, at the end of the last video. So part A, if you have the following distinct eigenvalues, lambda 1 through lambda k, distinct meaning there's no repeated eigenvalues in this list. And if v1 through vk are eigenvectors corresponding to each one of these, then the set of those eigenvectors is going to be linearly independent. So in a certain sense, what that means is that the eigenspace that's corresponding to each one of these eigenvalues, remember the eigenspace is the vector space containing all the eigenvectors that correspond to whichever eigenvalue we're looking at, plus the zero vector. Essentially what this says is that none of these k eigenspaces will overlap except for the fact that they all contain the zero vector. We don't need to dig that deep into that idea, but that's kind of what this is saying. Part B says an n by n matrix with n eigenvalues, that was a typo there, I crossed it off and said values, is diagonalizable. Okay, so if you have as many distinct eigenvalues as you do rows or columns in that square matrix, then you can diagonalize that matrix. So we're going to prove A. B is an immediate consequence of this. So we're actually going to prove this by creating a contradiction, doing a proof by contradiction. So we're going to assume the opposite of what it is we want to prove. We're going to assume that v1 through vk, this set that we defined up here, is linearly dependent. Okay, now we're going to start by looking at subsets of this. So I know that a set containing one and only one vector is always linearly independent. We proved that a while back. So I know that I can find a subset of this that's linearly independent. I could go as small as just choosing one vector. But let's try to choose the largest possible integer such that v1, I'm going to call that largest integer r, v1 through vr is linearly independent. So starting with the first vector here, I'm going to keep putting more and more vectors, v1, v2, v3, and so on and so forth, until I get to the largest possible set such that this would still be linearly independent. Now I know that r can't equal k because my assumption here is that vk, the set containing all k of these, is linearly dependent. So this has to be some value that's less than k, which is what we're saying here. Okay. If r is the largest integer such that this set is linearly independent, then if I put one more vector in there, vr plus 1, then it becomes linearly dependent. So we're going to run with this. So if that's the case, there exists scalars c1 through cr1, not all of which are 0, such that the linear combination of those vectors with these scalars is equal to 0. That's the definition of linear dependence. Not all of these constants would be 0 in this linear combination. What we're going to do is take this linear combination that's set equal to 0, it's an equation, multiply both sides by the matrix A. And then we're going to use the fact that these vectors aren't just any vectors, but in particular, they're eigenvectors corresponding to specific eigenvalues of A. So if multiplying both sides by A, because the right side is 0, A times the 0 vector is just going to be the 0 vector. On this side, I already distributed the A into each term and used homogeneity to bring the C's out to the front. Okay. Equivalently, what I can do is group up each of these AV1, AV2, AV everything, and change them into lambda 1 v1, lambda 2 v2, because these are equal to each other. That's what it means for lambda 1 to be an eigenvalue of A, with v1 being a corresponding eigenvector. This would equal this, and so on and so forth down the line. Okay? Now, if I were to it says if we multiply the previous equation, by previous I mean the one that we got way up here, c1 v1 through, this linear combination that was equal to 0. If I multiply, I think We wanted this. Yeah. Oh, no, sorry. That was correct. Doubting myself. Okay, if we multiply this equation, this guy right here, by lambda r plus 1, so that each term gains a factor of lambda r plus 1, and then we subtract that from this equation right here. Notice we have r plus 1 terms in each linear combination, and they match up v1 with v1, v2 with v2. So we're basically just subtracting the scalars. You would get this. Okay, so notice that the terms now, they look like c1 lambda 1 minus lambda r plus 1 plus c2 lambda 2 minus lambda r plus 1. And if you notice, the vr plus 1 term has disappeared. The final term here is vr. The reason that happens is because this term in this equation right here is going to exactly match this term once we multiply it by lambda r plus 1. So those are going to cancel each other out completely. It goes to 0, and we end up with one less term on this linear combination right here. And this is the key thing that's going to make this contradiction show up. So by the assumption that we made about that positive integer r, this set, v1 through vr, is linearly independent. And we have a linear combination of those v1 through vr that's set equal to 0. If it's linearly independent, that means each of these scalars has to equal 0. Okay? Now, because we assumed that all of the eigenvalues in each one of these, all the eigenvalues, lambda 1 through lambda k, are distinct, the difference between any pair of them can't equal 0. That would imply that, for example, if this was equal to 0, that lambda 1 is equal to lambda r plus 1, or similar for any one of those. So none of those things in parentheses can equal 0. That means if all of these scalars are 0, it must be all of the c's that are equal to 0. Okay, but if we go back to this equation that we had up there, c1 v1 plus c2 v2 plus all the way through to cr plus 1, vr plus 1 equals 0, plugging in all of the c1 through cr equal to 0 into this linear combination on the left-hand side leaves me with only the last term here, cr plus 1, vr plus 1 equals the 0 vector. That's what we have right here. What that implies, because remember, eigenvalue or eigenvectors are non-zero. So if this product is equal to 0, it must mean that the scalar itself, cr plus 1, is equal to 0. But that creates a problem, because if you go back to where the cr plus 1 came from in the first place, all the way up here, it's the last scalar in the linear combination of these vectors that's equal to 0. And we just established that all of the c's now, including the cr plus 1, would have to equal 0, meaning that that set actually is linearly independent, not linearly dependent. That creates the contradiction that shows that our original assumption that this entire set v1 through vk had to have been linearly, sorry, I was pointing where you can't see. This set can't be linearly dependent because it leads to that contradiction. Therefore, it's linearly independent. Okay, so with this in mind, now we have this result. An n by n matrix with n eigenvalues is diagonalizable. And if you remember in the previous video, we had this theorem here where we said if A is an n by n matrix, then A is diagonalizable if and only if A has n linearly independent eigenvectors. Well, if there's a total of n distinct eigenvalues, then we can find a set of eigenvectors corresponding to each one of those, and according to this theorem up here, they would be linearly independent. Using the previous theorem, that gives us that diagonalizable property. So how then do we use this to come up with, or how then do we use this to actually diagonalize a matrix? So we describe it in a three-step process. The first thing we do is we have to make sure that our matrix is diagonalizable in the first place. There are lots of matrices, square matrices even, that are not diagonalizable. So it's not something that you just get for free. The way that we confirm that it's diagonalizable is we have to find n linearly independent eigenvectors for our matrix. And we can do that by forming a basis for each eigenspace. We've talked about how to do this back in 5.1. If you can find a basis for each eigenspace for that matrix, one basis for each eigenvalue that it would correspond to, if you end up getting all of those bases and throwing them into one big set, so taking the union of all of those bases, if you have a total of n vectors in that set, then those n vectors are going to tell you that this is a diagonalizable matrix. If there's not that many, if there's less than n vectors, then you can't diagonalize the matrix. And we'll do an example where we're going to illustrate this. Okay, so the next thing you want to do, once you've found those bases for your eigenspaces, you're going to take all of the vectors across all of those bases and turn them into columns for this matrix P. That's going to be the matrix that diagonalizes your matrix. Okay, and then if you want to compute the diagonal matrix that is similar to A, you find P inverse as well, and you multiply your matrix P inverse A times P. That should give you your diagonal matrix D. Okay, so that's also because of those similarity invariants, you're going to see that the eigenvalues that you've already computed for A are going to show up as the diagonal entries on that diagonal matrix. So let's make this a little bit more concrete with an example. Okay, let's see. So for this one, we want to find a matrix P that diagonalizes this matrix here. It's a 3 by 3. This one turns out to be diagonalizable. Otherwise, this wouldn't be a very interesting problem. Now, it's a somewhat lengthy process because we have to find bases for the eigenvalues that correspond to this matrix, which means we have to find the eigenvalues as well. And because this is stuff that we did in 5.1, I'm not going to go through every single step for finding those eigenvalues, computing that the base for the eigenspaces. So I'm just going to kind of outline some of that stuff. So the first thing I want to do is find the eigenvalues. That means we compute the determinant of lambda I minus this matrix, which would look like lambda minus 2, 2, negative 1, 1, lambda minus 3, 1, negative 2, 4, lambda minus 3. Okay, now that's a 3 by 3 determinant. There's a lot of simplifying, and then there's going to be some factoring to do to get this thing to factor down the characteristic polynomial where we can find those eigenvalues. But in this case, let's see, I did this one ahead of time. Where did I put it? Oh, here we go. This one, if you expand this and then factor the result, we end up with lambda minus 1 squared times lambda minus 6. Okay, so that's your characteristic polynomial. That means that I have two eigenvalues, two distinct eigenvalues for this matrix, 1 and 6. Okay, so starting with lambda 1, or lambda equals 1, remember you want to find a basis for the eigenspace that corresponds to this. And this is where I'm going to skip some steps. I'm going to go straight to the basis, but you would do this using the technique we talked about in 5.1. So the basis that, or a basis that I can get for this eigenvalue is 2, 1, 0, negative 1, 0, 1. And then for lambda 2, or sorry, my second eigenvalue, which is 6, we get a basis that contains only one vector, 1, negative 1, 2. So that's the eigenvector that corresponds to 6. In light of the previous theorem that we talked about at the beginning of this video, if I take all three of these vectors and put them into the same set, it's guaranteed to be linearly independent. So that means I have 3 linearly independent eigenvectors corresponding to the eigenvalues of this matrix, and it's a 3 by 3 matrix. So that tells me that my matrix P, that's going to diagonalize this matrix, is this. 2, 1, 0, that becomes my first column, 2, 1, 0. Negative 1, 0, 1, is my second column, and then 1, negative 2, 1, negative 1, 2. Okay? Now the problem only asks us to find the matrix P. So technically we're done here, but if we wanted to go the full length of representing A as, you know, P times the diagonal matrix times P inverse, I would need to also find P inverse, which, remember, you can do that with the inversion algorithm, that application of Gauss-Jordan that we talked about in chapter 1. If I were to do that, I'm going to find that P inverse for this example comes out to 1/5, 3/5, 1/5, negative 2/5, 4/5, 3/5, 1/5, negative 2/5, 1/5. Okay, which means if I wanted to now represent A in a way that shows that it's diagonalizable, A is going to equal P, which is 2, negative 1, 1, 1, 0, negative 1, 0, 1, 2. The diagonal matrix here is going to have my eigenvalues as its diagonal entries, but you have to make sure you're getting the order correct. So the way that you know the order is it comes down to the order that you put the columns in. Notice if I had worked my bases here by finding this basis first followed by this basis, I probably would have made this my first column and then these my second and third columns, which would have been fine, but what it would do is reorder these diagonal entries here. So as I go from left to right, column 1, 2, and 3, the eigenvalues that these eigenvectors corresponded to are going to be the ones that show up on the diagonal entries. So these two, columns 1 and 2, corresponded to the eigenvalue 1. That means my first and second diagonal entries should be a 1. This third eigenvector right here corresponded to the eigenvalue 6. So that's going to be my third diagonal entry. Zeros everywhere else because it's a diagonal matrix. And then my inverse will show up over here. 1/5, 3/5, 1/5, negative 2/5, 4/5, 3/5, 1/5, negative 2/5, 1/5. Okay? That'll do it. We'll take this concept a little bit further in the next video.